So, welcome to MAE 209, Probability and Statistics. My name is Richard Kohar, and this is lecture 24. As we're nearing the end of our series of lectures. So we're still working now in probability. We finished probability, and now we're working with statistics. And what we're going to be looking at today is maximum likelihood estimators. And we just need to also maybe just do a little recap from what we did last time. So recall from last time. What we had was the idea of unbiasedness. So we had an unbiased estimator. So again, if we had some random sample, and they each have a PDF or a probability density function. We have f of x for some parameter, theta, and we're going to use t to be our statistic. So we have some t, which is a function of our random sample. So again, remember, a statistic is just a function that takes the sample and it outputs it to a real number. So we say that t is an unbiased estimator. If now in the chat, what do you think I would write down for this? What is the definition then? That t is an unbiased estimator of theta if, what's the condition? Yep, that's good. And again, our t, some people are writing theta hat or, yep. So we could be thinking t, like I was writing it as t here because I was using a statistic. But yes, I could also be thinking of it also the alternate notation we were using was the theta hat. Yep. So if, some people are writing that right. Yeah, some people are also saying, yeah, these are all good ways of expressing it. So you could say if the expectation of the statistic is 0, or sorry, is equal to theta, or you could also write that as the expectation of theta hat, which is our estimator, is equal to the actual estimator, or the actual parameter that we're trying to estimate. Good. And then the bias that estimator is biased. And the bias is just how much there is. Kind of the difference between the expected value of the estimator and the true. So this kind of gave us an idea of what we would like a good estimate to be. So this is kind of like what we were talking about, was trying to define, like mathematically, what we're trying to do is we are trying to describe this goodness of an estimator. So again, we're describing, but what the real problem is now we're getting to the issue of how do we build one? Right? So we're kind of getting into this idea of how to construct one. So again, we had lots of other estimators that we had thought about, like we could use any of those ones that we had from descriptive statistics. So that's one way we could do it. Like we could use descriptive statistics. And then check. But that kind of negates the whole point of doing your first year calculus course. So that's the next step that we'll say is, here's another one. We could just use calculus. And construct one. And then we'll still have to check if it's biased or unbiased. But this is what we're going to use, calculus. So we've gone from, we described what an estimator is, like a goodness of one. We'd like something that's unbiased. We need to figure out a way to build one. We can use descriptive statistics, but it's not always good. We could use some calculus, and from calculus, well, remember we had talked about, probably in 101, the idea of optimization. So let's say that I have some function like this. Oh, and I'm not drawing my function yet. I'm just drawing my axes. So I have some function, and let's say I have a concave function, just an arbitrary concave function. So just as a reminder, what does it mean to be concave function or concave down? What does that mean in terms of calculus? What does it mean in terms of this function? I think everyone is starting to get the idea. Yes. So again, this is in this example here, this is a concave function. It's concave down for the entire domain that I drew it on. So what it's saying is that if I take the second derivative, that it's negative. And this is concave down for all x that I was drawing it for. And because of this, I can use this, basically I can use this as a, I think we called it the concavity test for maximization. All right. So if we know that the function is concave, then there must exist some maximum point, right? So what we do is we can look at, so this is the second derivative here, but the first derivative, if I just kind of pick some points here, that's where the tangent is. You can see the slope is there. We have a slope there. If I drew it right here, that's what we want. Again, the tangent should be just touching the curve, not overlying it. So at this point here, yes, that's where our derivative is equal to 0, and that's our maximum. Let's give it some kind of like, let's give it a little accent so that I know what I mean. So if I take that the point x is a maximum. Okay, so that's what we learned from calculus. That's what we kind of want for an optimization. Very quickly, so what we want to do then, taking that, so we have calculus, we're going to do, so what we would like is a good estimate of the parameter theta, and again it's unknown, would be that the value of theta. We're going to say maximizes let's say the probability of getting the data we observed. Okay, so we want to maximize the probability. So what you can think of it is it's a way of finding or fitting a theta that best represents that data. So again, you are now thinking of it as theta, as optimizing that value. So this is when we started to look at this in the 30s, and I believe it was Fisher who was doing it. You know, they started to try to maximize this. So again, the probability, and they would start to use the probability density function. They found that this was very cumbersome. They needed to do some calculus trickery. So what they did was they transformed the problem. So instead of using the probability, just the straight PDF, and maybe I'll just write that underneath here, the PDF. What they used instead is what we call likelihood. So they were using the likelihood. Now, people, you know, the average person on the street will say likelihood or probability. These are interchangeable terms, but in fact, they're not. So when somebody says, what's the likelihood of something, they probably mean probability. But in math, because of this, we're trying to maximize something. The likelihood actually means essentially the log PDF. So what we do is we apply the natural logarithm to the PDF. And that gives us some nice properties that we can exploit and manipulate. Okay. So I was talking about the likelihood. What is the likelihood? So again, we have some random sample. Now in the textbook, they kind of dance around not having to use some of the notation. They end up writing out a lot of density functions and kind of writing out in full. We kind of need this some of this notation, and I think it helps to understand and represent this concept a little better. So for a sample, we have x1 through xn, and it has some sort of PDF, probability density function. Again, this also works for the discrete case as well. So again, it could be a PMF. It's not just restricted to the continuous case. We can also work with kind of an idea of calculus in a discrete sense. So we have a PDF, and we'll use xi for a PDF, and that's for each random variable xi. Okay, so we have that. We have a random sample. So then what we do is we want the joint probability mass or density function. So I'll come back to. So what I was saying here is I have my probability, my PDF, and they're joint, so we're going to multiply them together. So I'm going to use the big capital Pi notation, and this is meaning the product. So that's all it means, is the product. So if we had sigma, that meant the sum. If we use pi, that means it's the product. And so you can think of this as this is what we call the likelihood function. So that's L of theta. Okay, so it's called L of theta. So, in light of the basic idea of maximum likelihood, one reasonable way is to proceed is to treat the likelihood function L of theta as a function of theta and find the value of theta that maximizes it. So then the optimization problem is to maximize L of theta. And so we're trying to maximize so we're not trying to maximize this function here. What we want is well, you could think of it as maximizing like this, but what we're really after is the theta. And that's what we call the argmax. So what that is saying in words is what is the theta that maximizes the arg meaning argument, so the argument that maximizes this function. So what is the theta that maximizes that maximizes the likelihood function. So basically that's what it comes down to. That's the whole premise of that. So we have this likelihood function that we've now expressed And this is the problem that we're trying to solve. And that's what we'll call our estimator there. Okay, that's what we want. So some people may be thinking, wow, that was a lot of theory. It could be a lot of theory, but you know, it ultimately is coming down to back to this idea of just finding the maximum of a function. So what can get a little bit more complicated is that we might not necessarily just have just a one variable function like f of x, but what happens is, what if there's a probability distribution that has two parameters? Well, that's where it gets a little bit more complicated. Like, we can think of the normal distribution that has both the expected value and the variance, right? We have mu and sigma squared. So that requires a little bit of setting up the equations, and then we'll have two equations, two unknowns, because we'll have to maximize for one parameter and for the other, and then have to solve. So like the normal. Okay, but let's try this with just one parameter first. Let's start simple. Okay, so let's do that simply for one parameter. So here's my example. So let's suppose we have a random sample. Okay, where we'll use that xi equals, we'll say 0 if, let's say, a randomly chosen cadet Now, what is the language profile that you need to have? Is that BBB? Yeah, BBB, okay. You know, proficiency in a, I know I wrote proficient. So let's say that they have, well, let's use 0 as being false. So if a randomly chosen cadet has not French Pro BBB, so they don't have it, and they have BBB. So assuming that each of these random variables are independent, meaning that one student doesn't affect the other student's likelihood of, or sorry, probability of having it. So assuming that they're independent, with an unknown parameter p. Right? And that would be, think of it as the probability of having BBB So the question then becomes, find, and so we use the shorthand or the abbreviation MLE. So find the maximum likelihood estimator of P Now, some people could say the probability, or some people would say proportion. Okay, so we're asked to find the MLE of P. So this is let's start our solution. So again, because we're assuming that they're independent, then they're independent and they're either 0 or 1. And I'm not sure if I had used this term before, but these are called a Bernoulli random variable. And that's where it's either a 1 or a 0. So you can think of this as like a very similar to, say, well, it's a simple version of a binomial random variable, which is, again, where you would have the number of trials. So just think of it as a binomial where n is equal to 1 and you have p. So you can think of it like that. So the probability mass function of each xi, so we have our probability mass function, so we used p, so xi, we have some, this is going to get kind of weird, okay? I know I'm supposed to use p for the PMF because it's a probability mass function, but just for the sake, for the time being, let's not use that p for the probability mass function. I'm just going to use f. So f is our function here, okay? Just to make sure that I'm confusing it with the p of the PMF and the p, which is the proportion of having BBB. So you would have, this would be either 0 or 1. So you can think of it as p, and you'll have 0 or 1 up top here. And you would also have the probability over here, which would be 1 minus that. Right, and again, xi would be either 0 or 1. And p has to be bounded between 0 and 1. I think I could include it or exclude it. It's up to you. But let's use closed. We'll leave in the possibility that everyone could have it or everyone doesn't. So it would be very boring. There would be no need if it was either 0 or 1 for the p. But okay. We'll have to maybe revisit this. So, therefore, the likelihood function, so we have our L of the estimator, we have p of x1, sorry, p to the x1, 1 minus p, 1 minus x1 times p x to the 2, 1 minus p, 1 to the 1 minus x2, dot, 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 all the way to p of x to the n minus p 1 minus x to the n. Okay. And then we can simplify this by summing up the exponents. So I get p, and then it would be p, and then we add those up, so x1, x2, all the way up to xn. Times 1 minus p. And then I would have, well, I would have 1, 2, all the way up to n, so I would have n minus, and then we'll have the summation. Oops, it looks like an X, but really I should write an I. So okay. Now, in order to implement the maximum likelihood method, what we need to do is find a P that maximizes this. So that's where we need to put our, start thinking about calculus, and we need to maximize the function. And what we're going to do is we're going to need to differentiate the likelihood function with respect to P. And so in doing so, we need to use a little trick that makes the differentiation a little easier. So just as a little side note, oops. And we have X and we have Y here. And what we have is we're going to use the natural logarithm. Let's see, it should hit at 1 here. So remember that this should be a vertical asymptote. Again, x equals 0 is a vertical asymptote. There's our ln of x. So let's just look at this. We have x1 and x2, and then we'll have f of x1 and f of x2. So again, if we have x1 is less than x2, then this function that we have here is showing that the values of x1 is less than the value of x2. So what we're getting at is that what that means is that the value of P that we're trying to solve for that maximizes the natural logarithm of the likelihood function is also the value of P that maximizes Okay? So that's what our trick is. Meaning that if I apply this transformation, I'm going to apply ln to the likelihood function, that it doesn't change it. So that, meaning that, well, it does, it's a transformation, but applying the ln to the likelihood function doesn't change the value of p that maximizes the function for the likelihood function. So that's very useful. That's the trick. So that's the trick. And why are we doing that? To the likelihood function? Makes it much more easier to differentiate. Okay, it makes it much more easier to differentiate. So again, it makes the differentiation much more easier. So what that means then, going back to what we have here, so we'll apply the logarithm to both sides. Okay. So I'll have ln of LP, which means that I'll have ln of all this stuff up here. So I have ln of P, and then I have, can anyone see now why I did this in the first place? What can I do now that I've applied the logarithm to this? Yeah, I can split them up into two terms, and someone also said, well, they not quite take out the exponents, but what I can do is I can bring them down in front. So these will come down in front of the term here. So yes. So like I said, this comes down in front just because of our rules of exponents with a logarithm. And I should be careful not to say that it's, here we go. Okay, so Then the next part is take the derivative. Okay, so we'll take the derivative. So I'll use just regular D. And I'll take the derivative over here with respect to P. Now what's nice about this is that that derivative then applies to each of these terms. So I don't have to worry about the summation of xi. The reason for that is because I'm taking the derivative with respect to p. I don't have to worry about it. So I'm left with just the summation there. And what's the derivative of ln p with respect to p? Yep, 1 over p. I'm just going to write the summation right over here as just p. Good. And same thing over here. I have this term n minus the summation of xi. So again, that's basically from a derivative, that's a constant. So we'll leave it as is. And taking the derivative of 1 minus ln 1 minus p is just 1 over 1 minus p. So there's our derivative. And then we're going to set that equal to what? What are we going to set this derivative equal to? Equal to 0. So maximizing p. So we're going to set that equal to 0. Okay, so now we need to come up with we can clear out this fraction here. So the way that we can do that is by we'll multiply through by, let's see, we'll multiply by 1 minus p and p. Same thing here. We'll multiply. Okay, so if I write that out then, what I get is 1 minus p, and I'll have the sum still. Okay, so that will cancel out here, and this will cancel out here. So I'm left with 1 minus p times the summation plus okay. Then what I need to do is expand that out a little bit. So I'll have the summation here. Then I'll have a minus p times the summation plus, I'll have np minus p times the summation I'm not quite. Uh-oh. Yes, thank you. Someone did catch that for me. Yes, yes, yes. Thank you. Yeah, so when we did take the derivative, I did need to use the chain rule. That's right. Because I have the negative p right here. So here's the minus. And just kind of fixing that up here. There we go. Okay, so with that, again, because we have okay. So that means I can cancel this out here. Bring the NP over here. And I'm left with over n. And so that is our estimator. So therefore, I should write that as p hat is equal to or we could also think of that as perfect. So that's it. So that confirms what we kind of thought would be a good estimator in the beginning. Again, it's just the proportion or the probability of having it. So what that says here is that if I have n cadets, what I would do then is if I had a random sample, what I would do is I would just take the average of it, and that would become the parameter for my p here. And so that's the end of that example. So is there any questions about that so far? So maybe what we should do is just a little summary then of the steps that I was doing so far. So a summary. So I have a random sample. So I have x1 all the way up to xn. Step 1, the likelihood function. Okay, so constructed. So let's say construct it. Take the natural logarithm. Of the likelihood function. Find the derivative. And set to 0. Then solve for theta. Now again, you will have to find the derivative with respect to theta. And this is for one parameter. That's a good question. This, in theory, also works for 2 parameters. And that's what we're going to do after the break. So I think this is a good time to take a 10-minute break, and we'll do an example of 2 parameters. We'll do it with the normal distribution. Welcome back. No, I was just writing out an exercise. So what I was just saying is here's an exercise where I have, just to try it for yourself, for one parameter, just in case you want a question to do after this lecture immediately. I was just saying that we have a random sample x1 all the way to xn. It's from the exponential distribution. And you can assume that each of these are, each xi are independent. Why is that important? Is, well, if it's independent, then you can multiply the PDFs or the PMFs together. Yes, PDFs together. And again, find the derivative. Well, construct your likelihood function, take the natural logarithm of it, take the derivative with respect to the parameter and set it to 0, and then solve for your parameter. And that will give you your maximum likelihood estimator. Okay? So that's my summary right here. That's just kind of like a remark. Here's my exercise for you. So I guess you could say that this is part A, and part B is it unbiased? Okay, and it's based on the example in the textbook. So just have a look at that, and if you get stuck on this, just have a look at that solution. So again, here's our summary. We have our sample. We'll construct a likelihood function, take the natural logarithm, take the derivative, set it to 0, solve for theta. Now, again, this also works for 2 parameters, but instead, like I said, you'll have partial derivatives, and you will have a system of 2 equations, 2 unknowns. If you had 3, you would have 3 equations, 3 unknowns. So let's switch over. Here's a new piece of paper. Okay. Make sure we number our pages. 6, 7. So this is now 2 parameters. And this is the maximum likelihood estimator of mu and sigma squared for a normal distribution. So right there, that could be just one question right there on an exam or on a quiz. Find the maximum likelihood estimator of mu and sigma squared for a normal distribution. Okay. So what we should do is recall what the normal probability density function is. So And instead we're going to use theta 1 and theta 2. And this will be for the mu. And over here, this is for the sigma squared. And so the PDF is we'll have xi, because we'll have a random sample. And I just replace my variables now with theta 1, theta 2. So it should be 1 over and again, this is squared. So one over square root of 2 pi, and also over the square root of the variance, well, 1 over, and this is really the standard deviation. We have the expected value, the exponential function. We have xi minus the mean squared all over 2 times the variance. And remember that our expected value should be from minus infinity to infinity, and the variance is positive, or well, non-negative. Actually, it's positive here in this case. So there we go. Okay. So what we need to do now is create the likelihood function. So instead of just L theta, it's L theta 1 and 2. We have the product. So again, assuming that each of the random variables is independent, we can then multiply them together. So again, you'll start grouping your terms together. And what you'll get is 1 over. So you'll have this like n times. So this will be theta 2. So it's a half times a half times a half. So it'll be n halves, or n over 2, times 2 pi. And again, this would be n over 2. Then we have the exponential function. And I'll have the minus 1 over 2 theta 2. And again, I'll sum together the exponents because again, I'm multiplying e to the x, e to the x. So I would just add up those x's, the exponents. So and it's theta 1 squared. Taking the log, or the natural, I gotta be careful that I don't use too much of a weird L, because that might look like a Laplace transform. So that's not what I'm doing, it's just L. So again, I can apply the ln of it. So then I apply the ln to it. Oh yes, when I'm writing exp, yes, that means, unfortunately, I have all this in my exponent. It's very difficult. So yes, so yeah, if you have like e to the xy, this is the same way as expressing it as like that. Yeah, it's just because I have all, this is quite difficult to read if I start crushing it inside of the exponent, like writing it as a superscript. So now I can break this up. I can apply the ln to each of these terms, and I can also bring the exponent down in front. So I'm left with negative n over 2 that's a good, yep. Yes, because I had written it as the square root of 2 pi. So yeah, I can put that there. Okay, so I have minus n over 2 ln 2 theta. I'll also have a minus n over 2 ln of 2 pi. And then I'll have this up here will come down in front. So I'll have minus, well, I could write it like this, And it'll be ln of e. And we know what the value of ln of e is, and so that's just 1. Okay. So the next step is to take the derivative. So but in this case, I'll have to break, like that's kind of like 2 steps here. I'll have to take the derivative with respect to theta 1 of ln of L and I also have to take the partial derivative to theta 2 and then I would have to set it equal to 0 and solve for it. So I'm using the partial derivative now, so partial with respect to theta 1 of the ln L of theta 1 and 2 so as I look across here, I'm going to take the derivative. I don't have to worry about this because there is no variable theta 1 in here. So I don't have to worry about that. I don't have to worry about this one because there's no variable theta 1 in here. So again, we treat that like a constant, so that's 0. Again, there's no change with respect to theta 1, so we don't have to worry about it. And this is what we're left with over here. I have to take the derivative of this. Okay. So if it helps, I have to take, essentially, I have x1 minus theta 1 squared, x2 minus theta 1 squared, all the way up to xn minus theta 1 squared. And again, I'm summing these up. So I can pull out this. Again, it's not a derivative. Like there's no variable of concern there, so I can bring that out in front. And then what I'm left with is I have 2 down in front times x1 theta 1. I have to take the derivative again. I've got to remember my chain rule. That's very good that Eric's pointed that out. So again, minus 1 here, plus, same thing again, 2 times x2 minus theta 1. Again, because the 2 came down in front, and then I have my minus 1 here. Okay. So what I could have done is I could have written that as the summation of I have two times x1 minus, or xi minus theta, and then I have a minus 1 as well. What else can I cancel? I could cancel out this 2 and the 2 here. Again, that reduces. And I have a minus. I can bring that out in front. And the other thing I forgot is, again, this should be a minus right here, so we need to remember that. I need a minus right here. So I'll have a minus 1 there, minus 1 there. So I'll have this minus 1 and this minus 1 cancel as well. Okay. Then what I can do is set this equal to 0. I can get rid of the theta 2, so I'm left with okay. Now I can expand this out, so I'll have my summation . It's kind of nice that I was able to get rid of that squared term here. So again, there's no square here, again, because it came down when I differentiated. And now I can apply that to each of these terms. And then solving for this still again. So what we did find was that our mu1, which was kind of our theta, and so there's a kind of our hat, is equal to the mean. So that's good. So you were able to do it for one parameter there. So there's for the theta 1. So then what you have to do now is repeat that whole procedure again, and taking the derivative with respect to theta 2, setting it to 0. So if we do it for theta 2, then we need to take the derivative of this one. I don't have to worry about this, but I do have to worry about this one as well, because here's the theta 2 over here. So I have the minus n over 2 ln theta 2. Don't have to worry about this one. So same thing, we go through when we take the derivative, we'll get minus n over 2 and then what's the next thing? So I have my negative here, that's good. Times 1 over theta 2. Then we'll need a summation. So no, I'll keep my negative here. So I just have to take what's the derivative of 1 over x then? That's a constant, so I'll leave that. Good, yep, so it's minus. So again, then that will become a positive. And so I'll leave the 2 down here, and we'll leave that squared. There we go. So all I have to do is just square that. Good. Set to 0. So we'll have 0 is equal to minus . So what I'll do is okay, so that gives me a common denominator, so I can divide that out. Then, again, I can just keep solving for it. And there we have it. And that should look fairly familiar because, again, mu1 is our estimate for our mean, or our expected value. So that is our estimate. This is our MLE. So there we go. Now here's a question. Is the MLE sigma hat here unbiased? Last question for the day. Is it unbiased? Exactly. No, because the variance has n minus 1. Yep. Perfect. Okay, well, practice problems for section 6.1 had been posted, but for this section will be posted today. Okay, so keep an eye out for that PDF. What section in Devore will we be covering in next lecture? That's a good question. I think as I just double check the book. We're going to do section 7.1, and then we'll be done. Done for this course. Okay, have a great weekend. Again, if you have any questions, feel free to send me an email at my RMC account. Otherwise, enjoy the rest of your day. Take care, everyone.